Hey everyone, welcome to week one of the Econometrics course. Now, this week, the material, much of it will be review, hopefully, and fairly simple. We're just going to go over some basic concepts about data and descriptive statistics and some things like that that we'll need for the rest of the course. But you do have work to do this week. You need to be working through the R manual. By the end of the week, please be finished through to section 3 of the R tutorial manual. And also, you have lab exercises. So you'll notice in the semester spreadsheet that I put out, you've got 12 assigned lab questions for Unit 1. So that'll take you a bit of time to work through those. So make sure you do that. Make sure you read the textbook as well. You'll find my lectures follow the textbook very closely. So the two will reinforce each other, but you do need to keep up with that. Okay, so get a nice sharp pencil ready and let's get started. Okay, everyone, here we go. We are talking about COOP Chapter 1, and it's going to be an overview of econometrics. And, of course, you really should have the textbook by now. Hope you do. We're going to have an overview of some concepts of econometrics. And so first of all, we need to figure out what does the word econometrics mean. So there are two components to the word. There's economics, and metrics, which generally means measurement or the use of data to characterize things. So you can think of it as the use of statistical methods applied to economics. And the statistical methods are almost always regression based. Now, regression is a great tool, which you're going to learn all about in this course. So, some questions. Let's think some questions that we might be interested in asking that we would need econometrics to help us answer. Are certain variables related? All right, we're often trying to explain with respect to economies why some things change and other things don't. So why is it that the population of Ontario grew so large but the population of Manitoba did not? Well, maybe that has something to do with the access to the export market in Ontario versus the access to the export market in Manitoba. So if you're going to try to develop that as an explanation, then you'd need to discover, is there a relationship between the amount of export activity and the population of a part of Canada. You might also wonder why income in some countries is higher than in other countries. Maybe that's related to the size of the capital stock, historically speaking, in a country. So as soon as you try to explain one thing by relating it to another thing, you need to, first of all, check whether those two things are even related. And that's a statistical question. So we use econometric methods for that. Next, how large is the effect? Okay, you might find that two variables are related. Maybe interest rates look like they're related to the exchange rate, but is it a big effect or not? So how large is the effect? That's an econometric question. Is it larger than chance? This is a bit of a subtle question, but it's really important in any kind of statistical analysis. So let's say that a regulation changes. Let's say the government puts in place rules that restrict the use of a certain pesticide. And then we want to see, did that cause the productivity of the agricultural sector to decline? Well, you might get the data on the amount of output in that part of the agricultural sector before and after the rule change, and they may be different. Maybe afterwards it's a bit lower, but then again it fluctuates, goes up and down all the time. So we need to figure out, was it a large enough change that we would call it statistically significant, meaning it's larger than what we would have expected just as a result of chance. And another question, if we have multiple theories or models, is one better than the other? Oops. Is one better than others? So here are 4 questions, 4 of the many questions that we would turn to econometrics in order to help us answer. The tools at our disposal. Well, if you're going to do econometrics, you need to have data. And as part of your setup for this course, I've told you to download a handful of spreadsheet files or CSV file. No, you're going to download the Excel files and convert them to CSV files from the course website. So you need some data to work with. Then we need estimation methods. Now this is going to be a new concept, and so let me just spend a moment explaining it. I'm going to close my window because someone's cutting their grass right beside me. Okay, an estimation method. You're all familiar with the idea of taking a group of measurements and calculating the average. Like, let's say you want to know what's the average height of undergraduate students at the University of Guelph. Well, you get a sample of students, get the height of each of the students, calculate the average. You are employing an estimation method. So you know that the formula for calculating the average is just you add up the total, divide by the number of students in that sample, and that gives you the average. Well, why do you use that formula? There are lots of formulas that you could use to calculate an average or a mean. Why don't you take the square of each of the student heights and add those up, and then take the average and then take the square root? Or you could trim the lowest and the highest off the sample, or you could take the shortest person and the tallest person and pick the midpoint. In different applications, people use different methods. That method, for instance, that doesn't sound like it makes a lot of sense, but the midpoint between the low and the high, that's actually how the daily average temperature is calculated in weather records. They don't take the hourly readings, they use the midpoint of the low and the high. So these are all estimation methods. And what you're going to learn in this course is the estimation method follows from the underlying problem you're trying to solve. So just to jump ahead a little bit with this, when you take the average, you're taking a midpoint of a sample where the midpoint is defined as the point where if you measured the distance from the average to all the individual data points in the sample and added up those distances, you get the smallest sum of those distances. And there's a bit of geometry involved. So it's a it's a calculus problem. And we'll talk about that calculus problem. And so you go through all those steps, and what you end up with is the simple formula for the average. In other cases, though, we'll want to pick a different rule. So instead of minimizing those distances from the estimator to the individual data points, we might decide to frame it as a probabilistic problem, which means can we write down a rule that has the maximum likelihood of being the right answer? Well, that's a different calculus problem, and we'll look at that one. And sometimes it gives you the same answer as another method, but sometimes it gives you a different answer. So an estimation method is going to be a rule that we apply to give us the best possible estimate of what we're after. And again, picking the height example, you say you go out and you gather 25 students and you want to use that sample of data to estimate the average height of undergraduate students at the University of Guelph. Well, one formula would be pick an average that maximizes the likelihood that I've got the right answer. Another formula, pick an average that minimizes the error that I'm going to make. And in that case, they both give you the same answer, but that won't always be the case. So an estimation method. And another little jump ahead here is we're going to use a method called the least squares method. So I'll just write that down here. Least squares. That'll be the one we use most commonly, the least squares method. And then we need testing methods. And the other term for this is inference. A testing method, this is also really important in econometrics. So you get an answer, you take your data, you apply an estimation method, it gives you a number, it gives you a coefficient value, and then you need to do some testing to decide, does this answer make any sense? And so we're going to learn a lot of statistical tests. So for example, here's another example for you, sticking with the height. So you've got, let's say you've got students in the arts program and you've got students in the agriculture program, and you want to know, are students in agriculture typically taller than students in arts? Well, you take a sample of one group and a sample of the other group, and then maybe the heights are a little different, but then you need to test, is it a statistically significant difference? And so to answer that question, we need testing methods. And again, there's going to be some underlying statistical theory that will explain how those testing formulas are derived and how we interpret them. All right, moving to the data that we use. The data can be organized as time series. So YT, so Y would be the variable name, and T is the subscript, and T would run from 1 to capital T. So that's the typical notation for a sample. Let me zoom in a little bit just to make sure you can see the character here. So we always give variable names. We use letters, usually X and Y. And then there's a subscript to indicate what type of data it is. So time series, and in this case T stands for periods 1 through T. So if you've got data on the inflation rate for Canada, you might have the annual inflation rate from 1981 to 2020. There's also cross-sectional data. So there we have Y, and we put a subscript I, and that indicates it's cross-sectional data, and I will run from 1 to N. This might be, for instance, let's say you have data on the unemployment rate in all 10 provinces. So capital N here would be 10, and you've got cross-sectional data in the 10 provinces, and unemployment rate differs or across 50 states in the United States. But at each point in time, you've got a cross-section of the data. And then if we put the two together, we can have what's called a panel data set, where we pool the cross-sectional and time series information, and then we'd have both subscripts. And you could think of that as being, let's say you've got the unemployment rate in all 10 provinces over the period from 1970 to 2020. So we're mainly going to look at cross-sectional examples and then some time series examples. Panel data methods will be reserved for more advanced courses. Now I'm zooming out again a little bit so that the rest of the page shows up here. Now there's a further distinction with the data. There's quantitative data, and that's just the usual data that comes in numerical form, just numbers. So for example, wage rates. So let's say collect data on wage rates for workers in different industries across Canada. So you're going to have a sample consisting of numbers. But that's not the only type of data that we'll come across. Let me just slide this up a little bit so it doesn't move off the bottom of the screen. There's also qualitative data. Now, quantitative should remind you of the word quantity. So in this case, it's a measurement. It's a measurement of wage rates or measurement of whatever. Qualitative data refers to the quality. And there we're thinking it's a characteristic that you either have it or you don't. So it's binary in the sense of the characteristic is either there or it's not there. So I gave you the example before of students that are in the arts program or are in the agriculture program. So that would be a binary distinction in the data. And you might have also public versus private sector workers. And you might have male versus female workers. So when you're putting your sample together, you have the quantitative data like wage rates, and then you also have binary qualitative indicators. We're going to do some analysis of income data in one of your assignments where you will use both the quantitative and qualitative measures. So, for example, is there a difference between males and females in the wage rates that they're earning? This type of data is also called a dummy variable. And when we get to using dummy variables, that's the term I typically use for it. But it's also sometimes called an indicator variable or a categorical variable. It's not important that you know all these terms right now. A dummy variable, and when we have a dummy variable, it's always recorded as a 0 or a 1. So you have to define which is which. So in the case of a data set where you've got males and females, you might have the indicator variable is defined so that it's 0 if it's a male and 1 if it's a female. So in that sense, it's quantitative because it's a number, but we're just using the number to stand for the quality in this case, or the characteristic. Okay. Now let me just zoom out a bit and we move on next to talking about some simple data transformations. Okay, data transformations. Sometimes you get the data in forms that you don't want to work with directly. So one of the common transformations we make is a percentage change. So you get a time series of numbers. Let's say it's the wage rates of workers in an industry, and then you're interested not only in those numbers but also the percentage change each period. So if you have the data in time series format, and you take yt and you subtract yt minus 1, and you divide by yt minus 1. So yt minus 1 is last period's observation. But if this was daily stock prices, then that would be today's closing price, and this is yesterday's closing price. And then you divide by yesterday's closing price, and that gives you the percentage change, so you can multiply it by 100 if you like. And then that gives you a series of numbers. Maybe it went up by 5% or down by 5%. Sometimes some econometricians like to use logarithms for this, and here the rule is that you can get an approximate percentage change if you take the log of the value at yt minus the log of the value at yt minus 1, and again multiply that by 100, and that's also a percentage change. Another data transformation is indexing, and this involves rescaling the data. So rescale the series to start at a common value. So let's say you're working on a portfolio of stocks, and you've got some stocks that are worth a few dollars each, and you've got other stocks that might be worth a few $1,000s each, and you want to compare how they've performed. Well, if you just graph them all together, you'll have a bunch of lines that are clustered right at the bottom of the graph for the low valued stocks, and then lines that might be up in the hundreds or thousands. And so that graph isn't too readable. So then what you can do is rescale everything. So you divide each of those series by the value at its starting point. So then each one starts at a value of 1. And you can multiply it by 100 if you want them to start at a value of 100. But then they all start at the same value, and then some of them you'll see they go up, and some of them maybe they go down, and you'll get details out of it that you couldn't see. So that's indexing, and especially helpful for graphing, but sometimes it's useful for regression analysis as well. Graphing methods. R is very good at graphing, by the way. You'll discover that. Time series graphs. So this is, you've seen lots of examples of these. This is just plotting the data over time, and you can see it goes up and down. It might trend upwards, it might trend downwards, but it gives you a quick overview of how that time series has behaved over time. Another type of graph is histograms. So these are usually used for cross sections. You've seen these probably for courses where you get the grade distribution, and so the histogram of a grade distribution starts at 0, goes up to 100, and if the class average is, let's say 75, then we kind of expect that the grades will be distributed in groups, most of them clustered around the mean, and then there'll be a few that are above and some below, and maybe some far below. Hopefully not too far below, but some of them below. That's a histogram. So it's that bar chart that's showing the distribution of the data. And you'll have a chance in an assignment coming up soon to draw a histogram using R. And so the issues with drawing histograms is you have to choose the bins. So these are called bins. So the size of the bins, and then you count the number of observations in each bin, and then you're plotting the frequencies against the axis. So the count the number of observations in each bin, and plot those are called the frequencies against the bin intervals. So that's how you do a histogram. And then another type of graph, put that over there, is an XY scatter plot. And this again is used oftentimes when you've got cross-sectional data, or any time that you have pairs of data and you want to see how one relates to the other. So if we have, let's say, data on income and level of education, and a very simple way of checking whether they're related is you got income and you got education, and then you plot the two together, and maybe the scatter plot looks something like that. So there's a tendency for people with more education to have higher incomes. Okay, now I talked at the beginning about estimation. Estimation means choosing the best value of a parameter. And a parameter is going to mean a coefficient in a model. So it's an algebraic component of a model. So choosing the best value of a parameter for a model. So let's go back to the height example. So our example, EG, stands for example, is expected height. Call that H bar. When we say expected, that's essentially the mean. If you walked onto a campus for the first time, you'll have an expectation of what the typical height would be. The people you meet might be a little taller or a little shorter than your expectation, but you have in mind an expectation, an expected value of the height. So let's try to estimate what that expected value is. Well, you have observations. So you're going to walk onto campus and take a sample, and you get the height of the first person, and then the height of the second person, and the height of n people. Maybe n is 100 people. You might find 100 people willing to let you measure their height. So now you've got 100 heights. And I use this term here, choosing the best value. Well, what's the best value? Given your sample of data, it looks like bot. Let me fix that. Best. What's the best value? Well, in econometrics, we usually start with and usually use a least squares principle. Usually follows a least squares principle. What's that mean? Well, you've got all these individual heights and you've got the expected height, and everybody's going to be different from the expected height. So each person, I, in your sample, will be a little above or a little below your expected height, the expected height. Let's say you've got a sample, and hello, and there's a tall one, and one more. All right, so let's say the expected height, I'll grab a different color pen here, and we have to figure out, we have to estimate the expected height. So that'll be h bar. All right, well, this one's a little below h bar, and that one's a little below. This one's above h bar, this one's above h bar. So everyone's a little above or a little below, and that distance is this deviation here. This is the error term for our estimate. So so we're going to take that, and now one thing we could think of doing is just adding up all these deviations and trying to pick the value of h bar that minimizes the sum of them. But we're not going to do it that way. We're going to take the square of the deviations. So we're going to square those deviations, and then we're going to add them up. And we add them up using, when we add a series of numbers up, we can use the addition notation here of the sigma sign. So that's I equals 1 to n. So what we've done here is we've taken these individual deviations and we've squared each of them, and then we've added them up. And I'll call that E. So so this is the sum of the squared errors in our estimate of the height. So the calculus problem is choose h bar to minimize E. So we want to pick the value of h bar that will minimize the sum of the squared deviations around h bar. All right, so as I mentioned, that's a calculus problem. So we take the derivative of E with respect to h bar. There's only the one unknown, so I don't need to use partials there, but I will anyway. So so if we take the first derivative of that with respect to h bar, don't panic if it's not immediately obvious how you would do this. But if you go back to your calculus, then you should be able to verify that that's the answer you get. We're going to use summations a lot in this course, so I'll come back to this a bit later, how you can work with summations and what you're allowed to do and what you're not allowed to do, but I don't want to stop for that just yet. So we've got this expression equals 0, so we can multiply, or we can divide out the minus 2. So then we have the sum of hi equals the sum of h bar, and I'll run off the bottom of the page here. So the sum of hi equals, now here you're adding up n instances of the same number. So that's just the same as n times h bar. And so then the last step here is h bar equals 1 over n times the sum of hi, which that's just the usual formula for the average, just add up the values, divide by n. Why do we use that formula? Well, because it solves the least squares problem. We add up the sum of the squared errors around our estimate. We minimize the sum of the squared errors, and in this case it gives us that formula for the average. Now up here I had a different type of data situation. I had income varying with education, and you look at that and you kind of think, this looks like we could draw a line through that data, and maybe there's a structural relationship where income is a function of education. It might be a linear function of education. Might be indeed. Well then, if it's a linear function, so we've got y equals a plus bx is a linear function. Well, how would we pick the values of, let me just focus in a bit here, how would we pick the best values of a and b? Well, hold on, because we're going to get there, but we'll use a least squares principle again to do that. We're going to pick the values of a and b that will minimize the sum of the squared deviations around the line, and that's regression. So we're going to get into that very quickly, and spend the rest of the course doing that, actually, or applying the formulas that we derive. Example of a model. Okay, so I mentioned at the beginning, or a little earlier, the idea of building a model, picking coefficients for a model. Now, let's say that your job, you work for a property developer, and your job is to model house prices. So, property developer going to put in a subdivision. You've got to work out the pricing of the houses, and the prices have to be offered to the buyers before the houses are even built. And so so the price will depend on the characteristics of the house. All right, so what you want to be able to do is sit down with the potential buyer. I can zoom in here a little bit. You want to be able to sit down with the potential buyer and say, what kind of house do you want? And these are the options. And okay, here's the price. And so one very simple model would be the price that you offer is going to be an average, just a single number, plus there'll be an adjustment if the house comes with a swimming pool. And so the adjustment will have a coefficient, we'll call it beta, and we'll have a dummy variable for whether there's a swimming pool or not. So di equals 0 if there's no pool, and equals 1 if there is a pool. So then let's say we pick the price P bar will be 400,000, and then beta will be 10,000. Okay, so then you sit down with the potential buyer, and you're going to say, well, the house will be 400,000, or it'll be 410,000 if you want a swimming pool with it. So where do these come from? And that's your job here. Okay, you work for a property developer. They're planning a subdivision, and you got to come up with P bar and beta. And so one way of doing it, of course, is looking at construction costs, but then also they're going to be sold in a competitive market. So you also have to pay attention to what people are willing to pay. And so it may be that what people are willing to pay will actually be more than the construction cost. So that's helpful to know. So to figure all that out, one thing you can do is go get house prices in that area, data on what houses sold for and whether adding a swimming pool made a difference in the house price. But there's a whole lot more to house, excuse me, to houses than just whether it has a swimming pool. So let's think about the other things that might be in our model. So there's going to be this sort of central average, P bar, plus we have beta. Now I'll put a subscript 1 for DI, so that's our swimming pool, and then beta 2 for L. What's L? Well, maybe this is the lot size. Okay, so people might be willing to pay more if you give them a bigger backyard or a bigger front yard or more space from side to side. And of course, there are lots more things, so let's add in BI, where B is the number of bedrooms. Okay, so you can fill in lots of other things. You know what houses come with. There's a number of bathrooms, going to be the floor size, going to be whether it's got a nice view of the mountains or a river or something like that. Lots of features of houses and lots of data that you can collect. And what you're going to do with the data then is figure out what are the best values of these coefficients. And so when you've done that, when you've figured out the best values of these coefficients, you've constructed a model. And then the model ideally would let you say, okay, given these characteristics of the house, I know what the right price is to charge for that house based on what other houses have gone for in that area. And the technique for figuring out these coefficient values, including this one, I called it P bar, but to make the coefficient, make the terminology a little more consistent, we'll usually just call that beta 0, so then we're just dealing with betas, or alpha, or anyway, you'll know when we get there. The technique for calculating the values of these is called least squares regression. Okay, and sometimes we will use what's called ordinary least squares regression, and sometimes we'll make it a bit fancier and we'll call it generalized least squares regression. Don't worry what those mean, we'll get to it soon enough. But the idea of least squares regression is picking the values of these coefficients that minimize the sum of the squared errors in your model. There's another rule that we can use that we will also see, although we don't use it as often. And in that case, if I go back here, so least squares is solving this problem, solving the sum of the squared errors. We could write down a different function, and that function would summarize the probability that we've got the right values of those coefficients. We'll see later what that function would look like, but suppose we want to maximize the probability that we get the right answer. Well, that would be called maximum likelihood. And in econometrics, we usually start with least squares, but there are some cases where we can't find a least squares estimator, or it would be too complicated, or there'd be other reasons why we don't want to use least squares. And when that happens, you can usually switch to maximum likelihood. And again, you write down a function that describes the likelihood that you've got the right answer, and then you pick the values that maximize that likelihood. And in simple cases, these two give you the same answer. So we'll talk about maximum likelihood, but not a whole lot in this course. All right, I think that's enough work for now. So we'll stop the lecture here, and next lecture we pick up with descriptive statistics.